This video will provide a conceptual introduction to Fourier series, help you understand what they are and why they're useful. We'll begin by asking the question, why does a trumpet sound different than a flute? And for those of you that have not listened to a trumpet or a flute lately, I have a bad recording of both a trumpet and a flute. So here we go. Here's the trumpet. And here's the flute. So the question is, why do these things differ? Well, one way to look at this is to look at the actual waveforms that are created by the trumpet and the flute. So if we do that, what I've done is actually taken a digitized sample of the waveforms from the trumpet and the flute, and in the spirit of complete and full disclosure, I have to admit that they were synthesized trumpets and flutes. And I've plotted these waveforms on this graph. So the top waveform is the flute. The bottom waveform is the trumpet. Now, both of the instruments were playing the same note, which means that they were both playing at the same fundamental frequency. The Fourier series will help us understand why, even though they were playing the same note and at the same fundamental frequencies, they sound different. The idea is that the Fourier series will allow us to decompose these waveforms into a fundamental frequency, which is the note you hear. In this case, I think it was supposed to be middle C, plus harmonics. And the harmonics are sinusoids that are at integer multiples of the fundamental frequency. And the different harmonics in the sounds determine what we hear. It helps us distinguish between, say, a trumpet and a flute. The way that we break these signals into their fundamental frequency and harmonics is by using Fourier series. The Fourier series coefficients, which we'll compute for these examples in just a minute, tell us amplitude and phase of sinusoids, which again are at the fundamental and the harmonic frequencies. And this allows us to, by knowing Fourier series coefficients, we can determine what the sinusoidal components of the signal are. The Fourier series coefficients can be computed mathematically for waveforms that you can express as a closed-form mathematical expression, or by a computer. These ones I've obviously computed by a computer. And it turns out that the Fourier series coefficients, at least for the complex exponential Fourier series, are complex. So I'll show you an example that has the waveform for the flute. So we still have the time waveform for the flute down here. And this is the time axis. And then we also have the magnitude and the phase of the Fourier series coefficients. Okay, and what I'm going to try to do is pretend like I'm a computer and try to show you the different Fourier series waveforms by hand, and then we'll look at what it actually looks like if you have a computer do it in just a minute. Okay, so I have a Fourier series coefficient at 0. It has a magnitude very close to 0. This is what we call the DC component of the signal, because it's a representation of the part of the signal that doesn't change as a function of time. And then these two terms represent the magnitude of the Fourier series coefficient for 1 and -1. These corresponding terms down here represent the phase. And it turns out that the magnitude and phase for the 1 and -1 terms give us the magnitude and phase of the sinusoid that is at the fundamental frequency of our waveform. And so, again, I'll try to draw this. My guess is that the sinusoid at the fundamental frequency looks something like this. You can see it goes up when the signal gets larger, and it goes down when the signal gets smaller. Okay. And then for each integer larger than 1, I'll have a harmonic. So the Fourier series coefficient tell me that I have a fairly small harmonic that's twice the fundamental frequency, so I'll ignore that for a minute, probably actually not draw that in. At 3 and -3, I have a very large harmonic. This value up here is quite large. In fact, this is the largest frequency component in the signal. So what that means is that I should have a term in this waveform that wiggles at about 3 times the fundamental frequency. So let's see if we can more or less draw that. And I'm a little nervous about this because this is not going to necessarily be easy. So let's guess that our third harmonic probably peaks about here and goes down, and then it would peak again here and goes down again, and it peaks again here and goes down again. Okay, so you can see that this is a sinusoid at 3 times the frequency of our fundamental. And what I can do then to start to reconstruct the flute signal, which again is this dark blue thing, is add the first harmonic to the third harmonic. And when I add them together, I'll get something that might look something like this. This is one of the reasons why we do this on a computer, is that it's a lot easier to do this sort of thing on a computer. So it might end up looking something like this. Okay, and again, this probably isn't a very exact plot, but hopefully, whoops, sorry about that little interruption, it gives you a feeling for how the Fourier series coefficients determine the magnitude and phase of sinusoids at the fundamental frequency and at integer multiples of that fundamental frequency, which again we call harmonics, to allow us to break a signal into harmonics. So rather than continue to try to pretend like I'm a computer and can do this sort of thing well, let me show you what we computed earlier and can now display. This is the time waveform. In fact, here, let's see if we've got an empty one here. Oh, this is the original time waveform for the flute and the trumpet. If I take just the first harmonics and plot those along with the time, or the fundamental frequency, I'm sorry, and plot those along with the time waveform, I get something that looks like this. So the blue line still shows the waveform for the flute and the trumpet, and you can see that I have a sinusoid that more or less goes up when the signal goes up and goes down when the signal goes down. Okay, if I add the fundamental frequency, the second harmonic, and the third harmonic together, I get something that looks like this. you can see that for the flute, I've almost got an exact match. The blue is the original waveform, and the red is the fundamental plus the first two, second and third harmonics added together. And you can see that I've started to reconstruct the flute very, very nicely. The trumpet, on the other hand, doesn't look at all like it's being well reconstructed. And so if you wanted to, you could say, well, we're done with the flute, but we still need to get this trumpet thing looking a lot better. So I can keep going, and if I take the fundamental frequency and harmonics, the second, third, fourth, fifth, and sixth harmonic, then I get something that looks like this. And you can see that now I'm approximating the trumpet fairly well too. So why do we need to have more harmonics to reconstruct the trumpet well than the flute? Well, if you look at the Fourier series coefficients for the trumpet, you get something that looks like this, where again for the trumpet, this is the magnitude and the phase. And you'll notice that I have fairly large Fourier series coefficients in terms of their magnitude for the first, the fundamental frequency, 2 times the fundamental frequency, 3 times the fundamental frequency, 4 times, 5 times, and 6 times. So that's why I have to use 6 sinusoids in order to fairly accurately reconstruct the trumpet, because I have my Fourier series coefficients are fairly large out to that value. So that's actually also the reason why a trumpet sounds different than a flute. It has a much larger set of higher harmonics, and these harmonics allow your ear to differentiate between the trumpet and the flute. So in subsequent videos, we'll talk about how to compute Fourier series coefficients and a lot more great information like that.